In traditional computers, everything runs on electrical signals. Tiny electrons move through circuits, switching on and off to represent data. This has worked well for decades, but it comes with limits. As chips become smaller and more powerful, moving electrons through wires creates heat, consumes a lot of energy, and slows down when data has to travel longer distances inside the chip. Photonic computing replaces those electrical signals with light. Instead of electrons, it uses photons. These photons move through optical pathways, often made of materials like silicon, but designed to guide light instead of electricity. The advantage starts with speed. Light travels faster than electrical signals in most practical conditions inside a chip. This allows data to move more quickly between different parts of the system. But the bigger benefit is not just speed, it is efficiency. When electricity flows through a circuit, it generates heat. That heat needs to be managed with cooling systems, which adds cost and limits how densely components can be packed together. Light does not generate heat in the same way. This means photonic systems can move large amounts of data with much lower energy loss. Another important difference is how data is handled. In electrical systems, signals are processed step by step. In photonic systems, multiple light signals can travel at the same time without interfering with each other, using different wavelengths. This allows parallel processing at a level that is difficult to achieve with traditional electronics. This becomes especially useful in artificial intelligence. AI models require moving massive amounts of data between memory and processors. In many cases, the bottleneck is not the computation itself, but the movement of data. Photonic computing addresses this by allowing faster and more efficient data transfer. There are already practical implementations being developed. Some companies are building photonic accelerators that work alongside traditional chips. These systems handle specific tasks like matrix multiplication, which is a core operation in AI. By offloading these tasks to photonic hardware, overall performance can improve while reducing power consumption. However, this technology is not a complete replacement for electronic computing yet. There are challenges. One of the main issues is integration. Most existing systems are built around electronic components. Combining photonic and electronic systems in a compact and reliable way is complex. Another challenge is precision. Light-based systems can be very fast, but controlling them at extremely fine levels for all types of computations is still difficult. Some tasks are better suited for electronics, especially those requiring exact logical operations. Manufacturing is also a factor. Producing photonic chips at scale with consistent quality is still developing. The tools and processes are not as mature as those used for traditional semiconductor manufacturing. In simple terms, photonic computing is not about replacing everything overnight. It is about improving the parts of computing that are currently inefficient, especially data movement and energy usage. The most likely future is a combination of both technologies. Electronic systems will continue to handle control and logic, while photonic systems will handle high-speed data transfer and heavy parallel workloads. This shift matters because the demand for computing power is growing rapidly, especially with AI. Improving efficiency is becoming just as important as increasing performance. Using light instead of electricity is one of the approaches that could help meet that demand in a more sustainable way.